We'll just leave it. Just leave it. Doesn't matter. I'll just do it with the next group. Okay. So how many teaching weeks do you have left after the holiday? 3?
3 or 4.
3, we have
4 weeks until the exams.
We have a reason week, yeah?
I don't know. Yeah, possibly, yeah. So I will be teaching you for 3 weeks. Good. 3 weeks of revision. And what I'll do is, maybe I'll just alternate, do maths one class, next class do physics. No.
Keep it as
the timetable. Why?
As we used to do it.
Oh, fine. So we'll start then on Monday with maths. Yeah. Okay. Quantum mechanics. Okay, can you write this down? Quantum mechanics. Got that, Ian? No paper, silly? Okay, you got this? Yeah. Have you heard of this topic before? You heard of it before? Ian? No. Okay.
It is the same as quantum physics.
Yes.
Yeah.
So yeah.
Okay. So let's just cast our mind back to this formula we had in fields, which was the Earth and the Moon, and then this is the force between the Earth and the Moon. This is Newton's law of gravity. And what type of motion do we have here from this force? Be circular. Nothing interesting there. Huh? Next one. I saw it? All right. The next one is Coulomb's law. And you have the same setup. You just like before, instead of Earth and Moon, it's proton electron, and the force is nearly the same. The only difference is charges instead of masses, but it's essentially the same thing. Agreed? So we expect the same type of motion. Previously I lied when I told you something. I told you that there is no smallest distance. But there actually turns out there is a minimum distance. When we look at the proton and the electron, we discover, unlike the Earth and the Moon, there's only certain orbits we can be in, which you probably know from chemistry anyway, the orbitals. This is quite strange when you think about it, because if the formula is the same as gravity, then the motion should be the same as gravity. And when we think about the Moon and the Earth, we can picture it being at any radius. You understand? Whereas when we look at the proton and the electron, we can have an orbit here, but we are unable to put the electron in between. And this is because distance, also like light and atoms, has a minimum amount, and then you can't have anything smaller than that. So we can, how can we see this? So maybe just, well, no, you don't need to write anything just yet. Okay, so what have you learned about the energy levels in chemistry? Or what do you know here? These are different energy levels. Did you know that? Yeah. And
when light comes,
we have, that's it, yeah.
Energy level, and the energy loss goes up with light from this one.
That's it. So you've done this in chemistry then, yeah. Yes, yeah. So these all have positive, negative, or zero potential energy. These values. What are they? Positive, negative, zero. These energies.
Negative.
Yeah, why? They're trapped, yeah. They need energy to be free. And they use this increase in energy, and when it's free, its energy is more precise than that. If it's free, its energy is energy is free? No. Not quite that. Zero. Zero energy means it's freed. So this increases until it reaches zero. These are all negative. So if you want to increase, you have to give it energy because it's negative. And the way we can give it energy, like you said in chemistry, is you can shine some light on it. The photon can hit the electron and try to knock it up. If the electron does not get enough energy, if it only gets enough energy to knock it up halfway, it won't go up halfway. It needs to get enough to go up a full level. It can't go in between. How can we see this? We can see this through some simple, very simple experiments. If you shine a white light through a prism, we've seen this in waves. We get this color, red, orange, yellow, green, blue, rainbow color here. Now, if we heat up a gas, so we have some very hot gas, and the gas is bright, so it's, there's light coming off of it, and we send this light through the prism. Unlike the picture here, we don't get all the colors. Not all the different wavelengths, frequencies come off of this one here. And why is that? So if we look at the picture here, okay. So let's imagine we have our proton and we have our electron here, and we have another electron here. So if the gas is very hot, what's happening to the particles? It has a lot of energy. Yeah. So if the potential energy here is negative, the potential energy here is negative as well. Negative as well, but a different value. Let's call this P1 and this one P2. So which one is bigger, P1 or P? Sorry,
P2 is bigger.
PE1 or PE2? Which is bigger? 2 is bigger. Yeah. So let's see. For example, here, if this was to fall down, does it lose or gain energy as it falls? It loses energy. So conservation of energy says to keep it balanced, it must. Conservation of energy says the energy isn't lost. So what happens to this lost energy? You might know this from chemistry. No, it didn't become kinetic.
Light.
Becomes light, yeah. So then some light is released here. How much light energy is released? Well, we know the formula is equal to HF, and that should equal the difference in the potential energies, which equals the difference in the potential energy. Yeah. Now, because these are at certain levels, it means these can only be certain values. For example, let's imagine at this level it was minus 1 electron volt, and at this level it was minus 2 electron volts, and this one was minus 1 electron volt. So how much was lost when it moved? 1 electron volt. So this makes a particular frequency. And you might say, okay, well, say I want a different frequency. Say, well, maybe that's not possible because maybe you need only half an electron volt, but you can't get a half because you either lose one or you don't lose it. You can't have these in-between values. So what's happening here is the reason so much of it's black is because the photons that are released, they can only be certain frequencies. There can't be any frequency you want. So that's why some of the colours are missing.
But what's the difference between the second and the last?
But I haven't gone to the last one yet. Yeah. I'm getting to the last one. So the last one now. Here you have a cold gas. So the cold gas doesn't shine like in the second one. Like, for example, air in this room. Can you see it? No. So, because the gas is hot, it's like a fire. It's, it's bright. It's like a fire. It's hot gas. Hot gas like so. Like the sun, yeah. So in the third one, it's cold gas. So if we want to see what's happening, we need to shine a light through it. So again, if you imagine you shine a light through it, some of the light will have the right frequency to knock this up a level. If the energy is right, for example, how much energy does this guy need to move up a level?
1
1 eV. So if this has the right frequency, what will happen? The energy will go into the electron and it will get moved up a level. So what happens to this light? It's gone. It got absorbed by the electron. If the energy is too small, will the electron take it? It will say, no thank you, it needs to give it enough to move up a level. So now, you have some areas which are black. These black areas represent the light not passing through, because it was the right frequency for the electrons to take it. So this is called an emission spectrum, because it's the light that comes out and not all the frequencies come out. And this is called an absorption spectrum because it's the light that shines through it, but some of it is absorbed. What is really important for you for chemistry and for engineering, which I think is really the most important thing about this topic, is these patterns are unique to the material. So for example, if this was hydrogen, it would have one pattern. If it was helium, it would have a different pattern. If it was a mixture of hydrogen and helium, it would have a different pattern. So in other words, this is like a fingerprint for the material. And this is how materials can be identified. Using some kind of spectrometer. Not a mass, is it a mass spectrometer? Or is a mass spectrometer something different? Mass spectrometer gives you the mass, of course. Sorry, what's this one called? It's something spectrometer. A light spectrometer, or have you done another type of spectrometer in chemistry? Anyways, I can't remember the name. One sec, I'm trying to remember the name. I'm going to go with an emission spectrometer. I don't know, something spectrometer. So you can put the material in the spectrometer, you could heat it up, shine a light through it or whatever you need to do, and get the pattern at the end, and then the computer can look at the pattern, check it in a database, and match it with something that's known. Question?
The gas and the second are both the same?
Yes, it is actually, because the pattern's the same. Yeah. It's just flipped around because in the second case it's releasing the photons, and in the third case it's absorbing them. Yeah. So the location of the stripes is unique to the material. Okay. Have you done this pattern, this spectrum business in chemistry? Not this pictures I'm showing you here. No, okay. Actually, come to think of it now, in the exam, they sometimes give you one of these diagrams, and they simply ask, explain, like for example, if they gave this one, they would say, explain why some regions of the spectrum is black. So here you would say, because the light at those frequencies were absorbed by the electrons, and the electrons moved up an energy level, and so the light wasn't released on the other side because it was absorbed. So I think it'd be good to, you don't need to draw this one, but the vocabulary you definitely need, and this diagram here, the difference between emission and absorption, you definitely need for the exam. So could you at least draw these two for the exam? Yes? You have a 2-hour chemistry class after this. Yes. Myself and Dennis and John were in the office yesterday, and we were outraged to discover that we have a meeting at 4 o'clock today. It's like, what is the holiday? Who has a meeting at 4 o'clock? So you get to go home at 4 o'clock?
Yes. Not that bad.
Nobody wants a meeting at 4 o'clock before a holiday.
Yeah, but you know, still a holiday.
I know.
Still nice.
Yes.
Cool.
Cool, technically. In this context, cool gas just means not hot enough to release light. You drew this? Yeah. Continue or not?
The answer for the explain.
Yeah, you just put it in your own words. So like what I would say for the absorption is the missing lights represent light that was absorbed by the electrons because they're the right frequency. And for the emission, I'd say the coloured lines represent the light that was released at the right frequency by the electrons. It doesn't have to be. The key difference that they're looking for is that in the emission spectrum, it's photons given off by the electrons changing energy levels, and in the absorption, the key idea is that it's missing light because some of it was absorbed by the gas. So the exam, they would want the students to see that emission represents light being released by the electrons, and then the opposite for absorption. Continue. I'll have to add that to your reference, Musharif. Slow writer. Okay, excuse me. Right. Energy levels. Okay. If electrons fall from high to low by themselves, then what happens? Photon in or photon out? If you think about conservation of energy. High to low, the electron is gaining or losing energy? Losing energy. Because it's becoming more negative. Go from high to low. So if it's losing energy, to balance it, there must be an energy increase somewhere else. The photon is released. This is the missing energy.
Which one has more energy? The one closer to the atom?
No.
The one for...
Yes. Yeah. So then the electron will emit a photon, release a photon. If an electron in a low orbit receives a photon with enough energy, what will happen? It'll absorb the photon and move up to the next level. I don't think you need to write this down because this would be well known from chemistry, right? Okay, so here's a very, very typical question here. Extremely simple actually. An electron falls from state 4 to state 3 and a photon is released. What is the energy of the photon? Yes, Musharif, it is as simple as that. You got your calculator? You don't even need to use your new calculator.
No, I need to.
What is it, 0.66 or something?
Yes.
0.66 electron volts is the answer, because that's the difference between the two energy levels. Continue?
Yeah.
Yeah. Right, now, an electron is in the ground state. Ground state is the name for the first and lowest energy state called E1. Here it's, that's broken, minus 13.6 electron volts. It receives a photon and jumps to energy state 3, which has an energy of minus 1.51 electron volts. So it goes from minus 13 to minus 1, roughly. This is an increase, of course, because you're less negative. And the question is, what is the frequency of the photon? I think you should be able to figure out how to do this. I'll do it in 1 minute, but I want you to try. Hint, you need the formula from the last class for energy of a photon. And I believe you have this formula from chemistry as well. You said you did it in chemistry. The formula that has the H in it, Planck's constant. So I'll just draw it here for you. Energy orbit 1, it is minus 13.6 electron volts. And then in energy orbit 3, it is minus 1.51 electron volts. And it jumps up to energy level 3 because a photon struck it and was absorbed. So I want to know what is the frequency here of this photon. Okay, so I'll give you a minute to try this. Don't forget to convert electron volts into joules. Did you do that? Good thing I reminded you. Okay. Yeah.
Then we take the answer to the difference.
Yes. You got your calculator?
No share of calculator.
Can I convert after?
After what?
After finding a difference?
Yeah. Get an answer?
2.9.
But the frequency?
Multiply 10 to 15. Okay.
Okay, let's have a look. So the change in the energy will be minus 1.51 minus 13.6 electron volts. So the change in the energy is the same as 13.6 minus 1.51 electron volts. Or if I multiply that by E, I have it as joules. And that of course should equal HF. So then F would be whatever 13.6 minus 1.51 E over H is. So let's calculate that. What number is H, please? Is it 6? I think it's 6, isn't it? .92 times 10 to the 15. Is that what you said? That's what he said. Yeah. Yeah? It's okay? Yeah? Alright.
How did we get the delta A minus 1?
Yeah, this one is bigger and this one is smaller, so the difference is the bigger minus the smaller. You know, like the after minus the before, basically. Okay. Now there's a couple of videos here which if you want to pause this and then check it later you can, but they're good videos explaining what's coming up next, but I'll try and explain it here by drawing. I don't actually need to explain much because you did the listening with me, didn't you? So what I was going to explain next is just what you learned in that listening, that active listening. So what's really peculiar, when you have your double slit, if you pass a wave through it, you've seen this already with Snell's law and Young's double slit experiment, that the picture you get on the wall, there'd be a bright spot in the middle, this is N0, then we have N1, N minus 1, N2, and minus 2, and so on. And you have a formula for this. It was, remember, N lambda equals U sine theta. If you fire particles through, like let's say footballs, whatever, some of them will go through the left, some of them will go to the right, and we'll get this picture. Yeah. Now, this is a very simple way to decide if what you have is a particle or if what you have is a wave. So, you would think, okay, an electron is obviously a particle. It's a small negative charged particle. So, if I have some electrons and I fire them through the wall, I should get 2. I don't get 2. I get the wave pattern. So this means an electron is a wave. So then people were confused by this and said, well, maybe there's some weird things happening between the electrons that is causing some of them to fire over here and fire over here. So what we'll do is, we'll put a detector here. Now, obviously this is very small, so it's not going to be a person, but I'm drawing a person to represent the detector. And here, a detector. And this guy's job is to say if he sees the electron here, and this guy's job is to say if he sees the electron here. So, when the electron goes by, he would say yes, no, no. And this guy would then have to say no, yes, yes, because it has to go through one or the other. And then, quite amazingly, the presence of the detector changes it back to 2, which is extremely unusual because the electrons then seem to alter their behaviour if they're being observed. So then you might think, okay, what we'll do is we'll let the electrons pass through, so they go back to behaving like a wave, and then at the very last moment we'll check before it hits the screen. And the idea is, okay, if it behaves like a wave when it goes through the gap, it should still continue behaving like a wave when it reaches the screen. And amazingly, with the detectors right before the screen, it goes back to being a particle behavior, meaning that the electrons were somehow able to communicate backwards in time to say, we will be detected in the future, go back to behaving like a particle instead of a wave. Okay, so that is very, very strange. And in the active listening you learned, even if you let the particles go through and you detect where they hit, but you don't look at the results until later, so you save the information on a file. So this is called screen, and then you save the detector information here onto a file called, I don't know, detector, something like this. If you open this file, that means you're detecting here, but of course it's happened in the past. So if you open this file, you're looking at which ones they went through, the left or the right. And then if you open this file, you can look at the image. Imagine this is like a JPEG, for example, and imagine this is like an Excel file of yeses and nos, for example. So you open this, and then you open the JPEG, and the image you get on the JPEG will look like this, because you're detecting it. But then the mad thing is, if you delete this file, and open this file, you don't get the particles anymore. It goes back to a wave picture, which, if you think about it, it's almost like the electron can change its behavior in the past if it needs to, if it knows almost that it's being detected, and so its behavior alters. Okay, this is what you call quantum physics. It's the behavior of particles, not just electrons, but protons and neutrons as well. And their behavior is completely not as expected.
Even protons?
Protons, yes, but not as extreme as electrons. And the reason is, the smaller the particle, the more extreme this behavior is. So because the electron is 1,000 times smaller than the proton, the effects are 1,000 times easier to see. Yeah. So, not just electrons, but every particle will behave like a wave if it's not being detected. And if it is being detected, it will go back to behaving like a particle. So, basically, you have what's called this sort of wave-particle duality relationship. So, in some situations, an electron behaves like a wave. In some situations, it behaves like a particle. But it's not just an electron. It's a proton, a neutron, every particle. So, that means, if an electron or any small particle acts like a wave, you might want to know what the wavelength of that would be. And deBroglie had a formula for calculating the wavelength of the electron when it's behaving like a wave. So the wavelength of an electron when it's behaving like a wave is equal to this constant we had last time, h, divided by p, and p is the momentum. What's the formula for momentum? Remember from mechanics, momentum equals mv. So lambda equals h over mv. Okay. Is this a big or small number? If you think about what's in the fraction. Small, because h is so small. So that means it's difficult to see the wavelength and so the wave behavior, because the h is so small. So I know it's quite difficult, but it's it's just an introduction to quantum physics. It is literally page 1 of a 300-page book on it, so it only gets more difficult after this. And you'll need this formula for the exam. A typical question in the exam will be calculate the wavelength of an electron moving with this speed. We'll probably have that as an example. Yeah, we do, yeah. Okay, can you write this formula down? This is the deBroglie wavelength formula. Yeah? Yeah? Continue? So we'll do an example now. So in this example, you have an electron gun. It fires electrons quite fast, 0.1 C, towards a screen which is 1 meter away. So the picture is exactly like what I have here. You have a slit and a screen. and the distance here is 1 meter, and there's a electron gun here, and it fires electrons out, and of course they travel through here, and since they're not being detected here, they'll behave like a wave. So some of the electrons will land here, some will land here, some will land here, some will land here, and so on. So you get sort of many dark areas here. I'll draw that a bit better. One in the center, one here and here. Like this. Okay. So question 1 is something you can do. What is the wavelength for this electron? So what is the wavelength of these electrons here? You have the formula, so you can calculate these. Oh, and I also tell you the speed is 0.1 c. So what's the wavelength? Got an answer yet? Got it yet? What number is C, please? 28? Yeah. 3 is electron. Yeah, very small wavelength. 6 is micro, 9 is nano, 12 is pico, I think. So 24.3 picometers. Okay, B. But I think it's probably easier just to leave it in the formulas in for the next part. Uh-oh.
2.4.
I'll just go back. 2.4 times 10 to the minus 11. Okay, B. These electrons are fired through a double slit of separation 10 to the minus 10. So the separation here is 10 to the minus 10. That's the small d here. And the question is, what is the angle of the first order? So that's the sine theta one, yeah, for the first order. So that's the angle to this order here. You're using the formula n lambda equals d sine theta. I want the theta. Go ahead.
How much is the D?
The d? 10 to the minus 10. Sounds reasonable. Sine inverse lambda over d. What was the lambda? 2.4, and the d is 13.9 roughly, something like this. Okay. Part C. What is the fringe separation? The S, yeah. This one? We call this S, don't we, in the formula? Oh, the formula. You have to use, oh my goodness.
D sine theta.
No, sine theta in this formula.
Then it's D small over D capital. Lambda or sine theta or sine.
Hang on, I'll tell you right now, just give me a minute. Lambda equals, oh my goodness, S equals, I just need to think which one is which way around. This is a small number. Oh, is it like this?
I think so.
So do I. Do you have the formula in your notes there? You're Googling? Ms. Sharif, are you doing something helpful or not?
No.
Can you just Google formula for fringe separation?
Lambda big over S rho. W equals lambda big over.
Say that again. W equals,
Lambda
yeah, capital over small, is it?
S. Well, it's going to be the same then.
Yeah, but just tell me how they have it and we'll rearrange it.
S.
Like this.
Yes.
Oh, and what are they using for W? There's the width here.
I think so.
Yeah, so it is the same there.
It is the
Yeah,
same.
yeah. Okay, so using this formula, get the separation there, please. Now, actually, this is 1 meter, so that's kind of convenient. So it's just going to be lambda over d, which, if you think about it, you actually have to work that out here. Yeah. I suppose if I just type in sine of what I have on the screen, I can get it. 6 over 25, 0.24. So 24 centimeters then. Yes. Okay. So what we'll do is we'll take a short break and then, like last time, we'll do these together. Okay, Ms. Sharif?
Yeah. I'm already having.
You're already ready for your break? Oh, goodness. Oh. Coffee. Dead, huh? Maybe you need more cold air.
Cold air.
Impossible. Impossible. Where's he at, Don? Canteen? Are you feeling awake enough now to continue? This is literally the last exercise in the course, and then we're doing revision. So if you can find the energy to do this last exercise, okay, we'll do it in parts. So there's 2 questions and 2 parts in each question. So if you can just do the A part first, and then I'll put the answer on the board. Be strong. This is literally the last exercise screen. Then it's just revision. Just focus on that. Come on, Adnan. I personally have no problems with that since it doesn't affect me. Yeah, but being awake or asleep here makes a bit of a difference. There's only 2 of you in front of me, so I can't have literally half the class asleep. Congratulations. 7 o'clock is the latest I can wake up to be on time. Who's so loud out there? Is it our students? Yeah, we've just started EAD. We're just doing 1A, and then I'm going to do 1A, and then we'll try 1B. Come on, Adnan. The first question just requires you to minus 2 numbers. No. Yes. 10.2. Now try the second one. Come on. You look like sleepy zombies.
I'm looking to the board, but I can't move.
23 is E, correct. Let's calculate. So, at the higher level, what was the energy?
13.4.
And the other one? 13.4 is the lower one, I believe. And the upper one?
3.6,
Yeah.
3.4 and 13.6.
And I said it fell. So it lost energy of 10.2 electron volts. That's part 1. Part 2 is what was the frequency of the light that was emitted. So HF equals 10.2 E. So F is 10.2 E over H. E over H, I actually had that a while ago. No. E over H times 10.2. What did you get, Iad? It's 2.47 10 to the 15. Hertz. Okay. That's one part A. Now on to part B. While in energy state 2, so it went to energy, so this was energy state 2, this is 1, and then while in energy state 2, a photon is fired at the electron, and the electron just about reaches energy state 3. Okay, so an electron moves up to energy state 3, which in this one is minus 1.51 electron volts. What is the frequency of the photon required? What frequency do you require for the photon to be at so it can move up a level? So just like before. In fact, it's exactly the same, except the only difference is you're firing the photon at the electron rather than the other way around. So calculate the frequency again.
So
Yeah.
minus m and multiply by e.
Minus 10?
3.4 minus 1.5.
Yeah, that's it. So I'll just change the numbers here, yeah? What's the after one? Minus 1.51, is it?
Yeah.
Minus 1.51 minus 3.4. I'll do it this way. Okay. So this time the frequency is 4.57 times 10 to the 14.
So I put them the example 4.56.
No, because look what's after it, 99998.
Yeah, so it's wrong because it's 4.56.
Yeah,
There is more.
yes. Yes. And if you forget the units, that will cost you a mark as well.
Yeah.
So if this question was only 2 marks, then you've got nothing.
Even to use everything.
Yeah.
Oh gosh.
Yeah. I had one student 2 years ago, and she got all, or was it he? I can't remember who it was actually. He got all the questions right, well not all of them, like 3/4 or whatever right, but didn't write the unit in any question. And this cost them a grade. And this grade caused them to miss out on their university choice. So I tell people every year, don't let this happen to you. Yeah, don't forget the units, okay? Right, next part is, when it's in energy state 3, a photon is fired at the electron and the electron is free. How much energy is required? So, now the electron is up here. I want to know how much energy must this photon have so that it can free the electron. Exactly, 1.51 electron volts. Okay, good. Yeah. Right, let's have a look at the second one now. Okay, let you try this one by yourself. And you know what, to help you a little bit, I'll just draw what the situation is. So you'd have some kind of electric field. There'll be a little hole here, and this is at a very high voltage. So you have your electric field. Electrons move in the opposite direction. So there's a little electron here, and the electron accelerates through the electric field and then is released. So it's moving really fast, and then it hits this material called tungsten, I think is what I have here, isn't it? Yeah. Now, we did the photoelectric effect. When a photon hits a metal surface, it could free an electron. how much energy does the electron need to be freed? We call this the work function. Do you remember this? We should read for you this
Yeah,
time.
it's the HF minus KA.
Yes, okay.
Formula.
Okay, fine. So, the opposite is also true, interestingly. If you fire an electron at a metal surface, it will release a photon, which I think is quite interesting. So, photon hits the metal surface, releases an electron, or vice versa, electron hits the metal surface and releases a photon. I suppose what really is happening is the electron hits the metal surface, it binds the metal surface and it gets a negative potential energy, and to balance it then a photon is released with the energy equal to what it lost when it bound to the plate. So what happens here is a photon is released.
So even if there was no light.
Yeah, it's created, the photon. It's spontaneous, It comes into existence when the electron binds to the plate. And the only thing I tell you actually is I give you the voltage here is 10 kilovolts. Yeah. And the work function on the tungsten is 7.2 times 10 to the minus 19 joules. And the first thing I want is not the frequency, sorry, the wavelength. Although you probably need to get the frequency first. Okay, work on this. What? No, Mr. Reese, please, you need to think about difficult problems and try to work them out. Oh, okay. My picture, I think, is better. Back to the picture.
I prepared the picture, and I don't think I'm going to do it.
Of course he does. Do you want a hint? Yep. The electron here is at rest. Does it have kinetic energy? No. It has potential energy. Okay. And then when it leaves, it's traveling with kinetic energy. Since it's left the field, it doesn't have potential energy. So the potential energy here equals the kinetic energy here. When the electron hits the metal plate, it then has a negative potential energy. You know what? This is just like the formula we did last time. Then, what was it? It was HF equals work function plus KE. So,
no K.
what the heck is that? That's KE. And here is the HF part, and where's the work function part? Here. The only difference is the picture is backwards. Previously the light comes in and the electron comes off with KE. Here the electron goes in with KE and the light comes off. Well, it's the same problem, just the time is backwards. So this formula you can use.
Why does it produce photons not taking this?
I don't know what the mechanism is to produce the photon. It can't really produce anything else. Like, what else can it make? A photon doesn't have... No, because...
If you want to.
Sound and... Well... Maybe it's possible sound and heat, but... There's not anything near the electron for it to transfer energy to, It's not like the electron can strike a neighbouring partner and warm it up, you know what I mean? It can only really be a photon because the photon doesn't have any mass, so to make it doesn't require any mass, it's massless, so... It could be heat, I suppose, but you would really need to have the right conditions.
To EV, electron volt.
But usually not. Photons normal here. What's wrong? You think you got it?
From electron volt.
There's no electron volts in this question. I gave it to you in joules.
From kilovolt
Yeah?
to electron volt and multiplied by E.
No, don't do this. Because that's wrong.
Then
PE equals minus K
Yeah, what was that? Good question. Potential energy here. You know, remember, I give you the hint to remember, okay? The potential energy here is a lot like potential energy mgh, but instead of m, it's not m, it's not mass, it's q. QED, remember? For potential energy.
Yeah.
But what was the formula for electric field strength? V over D, so it's QVD over D. So the other formula we had was QV. Now, do we know the Q? Yes, we do. What is it? I said it was an electron.
Oh.
So the Q is E. And the V? 10,000. So 10,000 E. This is what you meant.
from that function like this in the exam.
But this was in the exam, that's why I'm asking it.
Right.
Yeah. This is how I got inspired for this one.
Yeah.
The reason I put it in the exam is because the reason I put it in the homework is because a lot of students were unable to do this in the exam because a lot of students got confused at the start here. So this potential energy is equal to the kinetic energy, which we can put into this formula we had last time. So we have HF equals work function plus kinetic energy, which is the same as potential energy, which is 10,000 E. So what am I looking for here? The F, isn't it? So F is whatever this is, yeah, plus 10,000 E over H. But that's F. Yeah. But we don't want F. We want wavelength. So what's the formula for wavelength? Yeah, lambda equals C over F. That's it. Because C equals lambda F. So what I'll do is just so I have one thing to type in on my calculator. Lambda is C over F. So that's C over that thing there. So that is HC over 7.2 times 10 to the minus 19 plus 10,000 E.
What happens to the electron?
It binds to the tungsten and releases a photon in the process. So now it's trapped in the tungsten. What number is E? It's, H is 6, isn't it? And C is 28?
Yes.
And E is 23, yeah. I got a very small value, yeah. 1.24 times 10 to the minus 10. Mushari. Get off the phone. What are you even doing? To who? Where? Oh, it'll feel better if it's not in your hand. Yeah? Yeah, that's better. Okay. Part 2. What part of the spectrum is this photon in? Such a small wavelength means such a high frequency, so what could it be? What part of the spectrum is this? What type of wave is it?
What are the types of waves?
There's,
The picture with the
Yes.
microwave
yes,
and
yes,
Electromagnetic.
yes,
Really?
yes. Remember I said you need to know. No, that's only half the answer. I want to know which part of the electromagnetic spectrum it is.
Can you go back to the
why do you need the close?
What part of the EM spectrum is this photon in? Have a guess.
Radium?
No, that's the wrong side. Wrong side is small wavelength, which means high frequency. It's an X-ray. This one is. Now, again, this was also part of the question in the exam. Because, right, listen, remember I told you you need to know that electromagnetic spectrum for the exam. Because they will ask you things like, what colour is this light? What? Now we'll do an exam question, we'll have a look at one here. We will. What?
We will not know. We have 3 weeks to do revision. We literally can think of that.
Oh my goodness, Miss Cherie.
Juries was telling me about Matthias is coming every day.
Yeah, but
Yesterday I was
What?
in the I think I slept like 2 o'clock and at 3:40 my sister
yes,
sent a message
Yes.
in the family group
yes,
and she woke me up
yes,
3:40
yes.
and I couldn't sleep for half an hour.
What do you want to know about quantum physics, Adnan?
I don't know anything interesting.
Well, we did. It was interesting, wasn't it?
It's not yet more.
Let's see, what else is interesting about it that you would need to know?
We don't have to know, not from the exam.
No. You want, okay, so we saw how particles can behave like waves if they're being detected or not. What I mean is, if a particle is being observed, so if you have a particle and it's being observed, there's my eye. It says, I am a particle. But if the particle is not being observed, so if the eye is closed, then it says, now I am a wave. So that's the first thing that you learn about in quantum physics, which is unusual. So you might be wondering, how does it know?
Is there a time limit if we took a video and then let's look after when we
No time limit. No time limit. It's as long as the information is still intact, then there is no time limit. It's not time dependent. Yes. Now, of course, in real life, it's not an Excel file or a JPEG file. I just made that for explanation purposes. But the concept is the same. A file, a storage device has one piece of information, and another storage device has another piece of information. Destroying this piece of information will cause this to behave as if it wasn't observed, even though it was observed at the time of the experiment. The only thing that's changed is the record of the experiment. Yeah. It's very difficult to accept that the particle has this sort of ability to alter the past almost to suit the current situation. Yeah?
If I with the detector
Yeah.
to watch the behavior
Yeah.
and put the second one to know if it behavior particle way.
Yeah.
It will behave the particle.
Yes.
But if I leave it my record it will behave like
Right, yes.
if I watch, like,
If you were watching it as it
if I save the file,
yeah,
2 files,
2 files,
and I watch the file,
yeah,
and I saw its particle,
yeah,
and then after I saw the particle, I saw the file,
yeah,
open the next file,
yeah,
and I click it,
yes,
and came back to the file that I watched,
yes,
and it was particle.
yes. Does it change?
Does it change?
No, because you've seen it.
As
Yes.
soon as you see
That's it. As soon as you've seen it, it's now, that history has been set. So, I know you open the file and you see, I look at it and it's like, oh, it's a particle. And then you delete the other file and open it again. It doesn't change into a wave. Because you've seen it already, it stays as it was, as a particle.
The electron work is a matter.
So
Yeah.
how did they know then that it changes if they didn't see the file?
How do...
How did they know that it actually changed if they didn't see the file that was fake?
Oh, because you would do this, I mean, like you would do this a couple of times, and sometimes you delete the file and sometimes you don't.
Okay.
So every time you delete the file, you get one picture, and every time you don't delete the file, you get a different picture. So obviously it must be changing then, you know. The other strange quantum behaviour, so you want unusual quantum behaviour.
Yes.
Huh?
1 by 1.
What's 1 by 1?
Electron.
Oh, if you start going in 1 by 1.
What's the gap?
Through gravity as well.
Like how many electrons per second?
It doesn't matter. You could put the electrons going in. What are you doing? You're getting cold.
No.
Sit down. You're distracting me. It doesn't matter how fast the electrons go in. You could send them in 1 per year, and as long as it's not being detected, the pattern that emerges will be a wave. You could send them in fast; it would be the same thing.
So an eye or a detector is the same thing.
Yeah, yeah. Now, of course, you can't. Too small to see, but the concept is, if you could watch it, yeah.
I know weird quantum here. I watched the video, and like it can act like it doesn't need to travel a distance from here to stay in that chair. Like
It just
yeah.
disappears.
Yeah, that's what I was going to do next. There's another thing called, 2 things. One of them might be what yours is. One called quantum tunneling. So, in real life, let's imagine this is life size. If you hit the ball against the wall, it will bounce back. And this will happen 100% of the time. But if instead you shrink it down, so instead of a ball, it's maybe an electron, and there's some barrier here, and the barrier is too big for the electron to pass through. So what happens is 99% of the time it will bounce back, but 1% of the time it will travel through the barrier. And the barrier is not broken, it has passed through the barrier. The barrier hasn't been damaged. That's not the reason why it's travelling through. It's travelling through because the particle is also kind of behaving like a wave. So it's almost like it leaks through the wall as a wave and comes out as a particle. Because it's not being detected, yeah. Yeah, so what's really happening is, since you're not detecting it, it's behaving like a wave. And the wave will, most of the time, bounce back like a normal wave does. But some of the wave leaks through, and you get kind of a small wave that passes through. And what that represents is the bigger wave means the particle is more likely to be here when you observe it. But sometimes it will be here if you detect it. So this is quantum tunneling. That is important for engineering. The reason it's important for engineering is because inside your computer, you know, you have your CPU, your processor. Processors are kind of pretty simple. What they do is electron goes in one side and comes out a different part. So it's almost like a processor is just like a road system, and the electron is guided through and then comes out a particular exit. That's all it really is. But imagine you have a road and the electron is moving through and it comes in here and it comes out here, that's all fine. But if it's small enough, the quantum effect increases, and 99% of the time the electron will pass through, but 1% of the time the electron will leak out, pass through the barrier, and maybe travel on a different path. Of course, this is a problem, and this problem is starting to happen because the processor is getting smaller and smaller. As you get smaller, the effect becomes greater. So there is some work, I think, in University College Cork or Galway, I don't remember which, in the West, where they're trying to work on building new processors of the future that limit the effect of the electron leaking through the barrier when it shouldn't. The one Musharraf is talking about, yeah, but you can't put it everywhere. Yeah. The one that you might be watched on YouTube, have you done spin in chemistry?
No.
Particle, like an electron said, it can be spinning upwards or it can be spinning downwards. So I'll give you an example with my phone. So this is the particle electron spinning up, so it's turning this way, and then this is it spinning down or whatever. It's not really too important. You just need to know that it's two ways for it to spin. It can spin up or it can spin down. So what's really strange is when you have two electrons together like this,
The same box or
together, the same container, and you don't know what the spin is on each, but you just know that the total is 0. So if this one is spinning up, this one is spinning down, and vice versa. That's all you know. But you don't know which one it is. So this one you don't know, and this one you don't know, but you just know the total is 0. Then what I do is I break the box, I give 1 to you, and 1 to me.
one still will be up and still down.
One will be up, one will be down. We don't know which. Okay. And then what we do is we separate the people a great distance. A huge distance. It doesn't matter how big, just there's a huge distance. And then this one here and this one here. So this one here, you look in the box and you discover it's spinning up. That will automatically make the other one spin down. Now you might say, well, that's not a big deal. But remember, this one is spinning up and down, and this one is up and down. We don't know which it is. And it hasn't decided which one it is because we're not detecting it yet. So it's still behaving like a wave. So the electron hasn't decided if it's spinning up or spinning down yet because it's still a wave. Then we detect it. When we detect it, we can see it's in here and we can see it's spinning up. Somehow, no matter how big the distance is, this electron is able to tell the other electron to spin in the opposite direction. So the distance is not important. The communication is instant. This is also important for engineering because this gives you a way to secretly send messages. For example, imagine we have some code we want to send. So let's say I want to send the code 0110. And let's say we call 1 is up and 0 is down. So let's imagine we send 4 electrons to Adnan, and I have 4 electrons here. So Adnan wants to send this message to me. So you have 4 electrons, and I have 4 electrons. And we open the box, and you see your one goes up, 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 down. So my one goes down, 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 up. And you want me to send a 0. So you say to me, keep the first one because you know the first one is right. It's a 0, it's going down. The second one I need to be a 1. Now since yours is pointing up, which way is my pointing? Down. That's not what you want. So you say, okay, change the second one. So then I go, okay, so I'll make this one a 1 instead. What message do you need to send for the third one?
Don't change.
A change again, isn't it? And for the last one? Keep. So, what is fascinating here is, this message that you send to me, this message could be public. This message is not useful, because since the person does not have this information, they don't know what they're keeping or changing, you know. If I said to you, change, 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 keep, nobody knows what message that will make, because you don't know what you're changing or keeping, you know. For example, if you had 0, 0, 0, 0, and I said keep, change, change, keep, the message would become 0, 1, 1, 0. Is that right? Keep, change, change, keep. Yeah. Keep, change, change, keep. Yeah. Something feels wrong here. This one we said change, didn't we? No, this last one was change as well. It's pointing up, and you want it to point down. Yeah, change. Yeah. This is currently a 1, and we want it to be a 0. So we have to tell the person to change it. Yeah? Alright, so let's imagine I have 0, 0, 0, 0. Keep, change, change, I would get 0, 1, 1, 1. That's not the right message. If I had 1, 1, 1, 1 and did the same thing, I would not get the right message. The only way I can get the right message is if I had this information, which is public information because you broadcast it over a radio or whatever, and this information, which is private information because only you have these electrons in your possession. You know, so this is the only 100% way to secure a message, because nowadays when I send you a private message, it's possible for a hacker to get this message. Even though the message is protected, a hacker could use an advanced computer to decode the message. But it's impossible here, because you need to have the original electrons and this public message to decode it. If you only have the public message, it's useless. And the other really great thing is, it's proven, it's a physics fact, that if you send these electrons to me, you know, I have 4 and you have 4, it is impossible for somebody to interrupt this and make a copy of it. As in, like, imagine you have, here's our electrons, he has 4 and I have 4, and you keep your 4, and then you give the 4 to me, so I'm taking it back here, and I have my 4 here, and I'm like, okay, I'll just wait for him to open his and send me the message. So you open yours, and then you say, keep, change, change, keep, and then I open mine and go, okay, keep, change, change, keep. But you might wonder, okay, let's say I left mine here, I didn't open it yet, I leave the room, maybe somebody comes along and makes a copy of this.
Yes.
But there is no way someone can make a copy of this without breaking it. Because there's a theorem in physics called the no-clone theorem, which says it's impossible to copy this box of electrons without breaking it. So if somebody did come along and made a copy of it and then left, my message will be broken. I can see that it's already been observed before you sent the message. These electrons are no good, I can't use them. Because for them to copy it, it means they open it. But if they open it before you open yours, then it breaks the link. You can only open it once, and if you open it once to make a copy, then you've broken the original. So this, believe it or not, is the way some banks communicate now. It's advanced technology. There has been some banks that communicate secret information this way. And what's also nice about it is the distance is no problem, because remember we said a moment ago, the electrons can send the information over any distance at once. On the moon, it's instantly sent.
But how do they connect together? Like when you put 2 together, they, like, one of them up and the other is down?
Nobody knows. Nobody knows what is the mechanism the electrons communicate to each other.
No, I mean to say that I have a box and the other has a box for the electrons.
Yeah.
And you have a box for the electrons. Then I open mine.
Yeah.
Why would yours change and not his?
Oh, because the 2 boxes have to have been originally one box. So if you have a box and you have a box, the electrons must have originally been paired together. And what you do is you separate them. Because remember a moment ago we said at the very beginning you have a total spin of 0 in the box. Yeah. This is what you might call advanced communication. Very advanced communication. Recently, this was tested between the space station in orbit, you know, the International Space Station, and Space Observatory on Earth, the sending of the messages between the electrons. So it works, as you can see, over whatever distance. Yeah. Can you go now? Oh my goodness. Isn't this not interesting to you?
No, can you take things before things?
Okay. Enjoy your holiday.
You do.
I will.
Do you do it in